I hope everything is fine. So we will continue this lecture, and in this lecture, we'll try to start with the topic we already had it, which was total internal reflection and all. We didn't do the numerical related to that, and then we will jump to the image formation. Okay. So now, first of all, what is as per Snell's law? We know that sine I upon sine R is a constant. So refractive index is equal to sine of I over sine of R. Plus it has another formula. What is that formula? Speed of light in vacuum or air divided by speed of light in medium. So basically, what exactly is a scenario? What type of question will come in? First of all, remember that this Snell's law will be used only and only, I mean, this especially can be used only when the body is, I mean, the light is going from light to any medium. I mean, from denser to rarer medium. It should go from denser to rarer medium. Whenever it goes from denser to rarer medium, that is the only thing you can talk about. I mean, this law will be applicable. If the light goes from rarer to denser medium, then the formula will be reversed. It will be sine R over sine I. So technically speaking, the numerator will always be the angle at the air side. Like for example, if the light ray goes from air to any medium, I mean, if light goes from any medium, because this sine I is for the air and this one is for the medium, right? And we know that in medium, the light will be reflected. I mean, refracted and bent towards the normal. So important thing is whenever light goes from denser medium to the rarer medium, this formula will be applicable when light goes from air to any medium. Remember that. But if light goes from any medium to the air, you can simply use sine R upon sine I. That is the reverse formula. Okay, so that is what the point is. Now, let's see the numerical based on that. For example, they say that light goes from air at an angle of 40 degrees. It goes from air is the what is the refractive index? So in that case, refractive index will be equal to sine I upon sine R, which is sine 40 divided by sine of 20, right? Now, when you do that, you can simply use the formula. You will see a very interesting fact about it. Now, what is that fact? Basically, sine 40 divided by sine 20. The value comes as 1.87. It is big refractive index, but I tell you one thing, refractive index value shall always be greater than 1 because the speed of light in air is maximum. Medium will always be less. So it refractive index technically tell you that how fast the speed of light is. Now, once you find out that value, if I, for example, ask you what is the speed of light in the medium, then you can use again that formula. We already know that 1.879 equals to. Now, speed of light in vacuum is constant. We know that. This is a value. Medium. You can simply move it in the, forward. Just cross multiply that. And you will get the value for this. Now, what exactly is it? Cross multiply. So the value is in medium, speed in medium will be 3 into 10 raised to power 8 divided by 1.879. So what it is? 3 divided by 1.879. So the value comes as 1.596 into 10 raised to the power 8 meters per second, right? So this is what we have, meters per second. So that is how you can use that refractive index formula for both the conditions, right? Now, once you understand with this, now go to, let's go to a topic, refraction. Okay. Now, remember there are two, three things. When you talk about refraction, the instrument which are used for the refractions are called as lens. Lens is a spherical shape, some sort of a sphere, and it's being made by the glass, right? So they are spherical shapes. There are two major kinds of lens which are used to for the refraction of the light purposes. One is called as convex lens, and the other one is called as concave lens. Now, what is convex lens and what is concave lens? This is a convex lens. Now, what exactly is a convex lens? You can see yourself. It is thick from the center and thin from the edges. Right? And then there is second kind of lens as well. What is that lens? This is a lens. What is this lens? This is the reverse of that. You can see that it is thick from the edges. Thick from the edges. Thick from the edges and thin from the center. Like that. Now, once you understand that, what further then? Now, there are a few things which we will discuss once we do the comparison. Now, let's talk about some very interesting facts about. There are some sign convention which you need to understand before we go into the details how the image is being formed. Convex lens, when the light is coming towards it, after a refraction, all the light ray meets at one point, and that point is called as principal focus. Principal focus is a point which is meant as when all the light ray after refraction meet at one point, we call it principal focus. The straight line, the horizontal line passing through the center of a lens is called as principal. Sometimes we do write it principal, PAL. Sometimes we do write it principal, but mostly we write it principal, this one, axis, right? That point, which is the center of lens at principal axis, is called as optical center. Now, another very interesting point is because this convex lens being moving all the light rays at one point or converging all the light rays at one point, this is also called as converging lens, because it has the ability to make all the line meet at one point, right? That's why we do call it converging lens, right? So this line, which is passing through the center as a horizontal line, is called as principal axis. The light ray which are passing like this, and after refraction, all meeting at one point, that point is called as principal focus. And the distance between optical center and principal focus is called as focal length, that is notified as a small f. Okay. Now, it converges all the light rays at one point. Now, in case of concave lens, this is very interesting. If you check it out, light rays after refraction, it diverges it, spread. Light rays are just spreading out. And when you move it backwards, it look like they're coming from one point. So technically speaking, they have a focus, but on the same side. And this is the optical center, the center of reference. So distance between principal focus and optical center is focal length. Now, there are two, three things. First thing is, because light ray after refraction become diverge or spreading out, so we call that lens as a diverging lens. Second important point is, if you see that actually light rays are not meeting at one point, in the convex lens, you can see yourself that light rays are meeting at one. So mostly 99% of the images formed by the convex are real and inverted. Now remember that. When you say real and inverted images are the images which are formed by the actual light intersection after refraction. Actual light intersection. Light is actually intersecting and forming the image. While in that case, if you check it out, light is not actually intersecting after refraction, but if by force you are bringing it in the backward direction, it look like they are coming from one point. So here the image form is virtual and erect. Now remember that one more very important. If the image is real, it should always be inverted. The real object is in upward direction. The image of the real image should be in the downward direction. So it should be inverted. There can be another example for that. That image which is inverted can be easily obtained on a projector or screen. While on the other side, in case of concave, because it's not real, it's not real, but it's a virtual and erect. First of all, it's virtual. It's not actually coming up. And erect means it's a straight one on the same side of the lens here. So it cannot be obtained on the screen, right? This is the major differences between convex and concave. Now, this is where the point is. Real images and virtual images. So we already talked about this real image, virtual image. There are two types of images. Now, there are different type of images. You've got enlarge, same size, diminish. Diminish means a small one. Same size means same as the object size. Enlarge is a bigger one. One type is called as upright. Upright means straight up. Real and virtual. What is real? As I just told you, it can have it actually formed by the real intersection plus it can be achieved on the screen. This is the virtual image. You can see it in the mirror. We already talked about this. It obtained on the plane mirror because it is not actually achieved by the actual intersection of that, but it just formed at the back of a mirror. It's a virtual image and it cannot be achieved on the screen or you can say projector, right? Now, few very important things to draw the image. So image formation by convex lens. Now remember that most of the images formed by the convex lens are real images. Okay. The first thing you always draw it to draw a principal axis. Always. Principal axis is a line that is not a real line but imaginary line which you always draw. On this line you will draw each and everything. Then you have to draw a lens, convex lens. It's like that. Right? And then you always draw a line, dotted line that tells you that your center is lying on this. Now, another thing, it's principal focus. The distance you will measure here from the optical center, let's suppose 1 centimeter, 2 centimeter, you have to further calculate or measure the distance from focus to 2F. So this is your F, this is your 2F, this is your F, same distance. This is your 2F. Remember that F and 2F will be on both the sides of the lens because lens can refract on both the sides. Now, to form an image, there are some properties of the rays that are passing through the convex lens. First ray, the ray which is parallel to the principal axis after refraction passing from the focus, always. So, the ray parallel to the principal axis after refraction passing through principal focus. That's the first one. Second ray, a ray that is passing through the center of a lens, which is called optical center, will not change its direction and will go straight down. So the ray, light ray, passing through the optical center will not change its direction after refraction. There can be another ray. It's a total reverse of that. A ray that is passing through the focus after refraction become parallel to the optical center. So there are three rays, but we mostly use the two rays only. Okay. Whenever you draw the images, remember that you always draw a principal axis. I always mark this focus 2F, F and 2F, and always draw the lens and then do it accordingly. Let's see the first case. Now there are cases how far you are placing the object. That is the first case. You draw a principal axis, you draw a convex lens, and you mark with them as F, 2F, right? Now, first case is when you place the object beyond. Now, if you check it out, the ray which is parallel to the principal axis, these arrow means the head of a object is in upward direction, right? A ray which is parallel to the principal axis after refraction passing through the focus. And the second ray that is passing through the optical center will not change its path. If you check it out, where these two lines intersect, you draw a line and the arrow is directed in the downward direction. Now, where the image is formed, this is interesting. image is basically where the image is. If I write the characteristics, image formed or image position is between F and 2F, right? And what is the size of image? Diminished, real and diminished. Why real? Because it's inverted. Diminished means very small, right? Now, what type of image is it? I mean, where exactly it's formed? What are the examples? You can have a micro for that. You can say micro, a very small image. Camera can be an example for that. So these are the devices which are using this particular setup to actually forming an image. Next is now start bringing the object further closer. All right. Now, what exactly is the situation? So let's quickly review that once again. That when an object is placed beyond 2F, the image formed between F and 2F, right? The image should be real and diminished, or you can say very small in size. And the practical example is micro and camera, the best examples. We got two examples. So